In this video, we're going to work two related rates problems. If you watched the previous video or one of the previous videos where we went through the related rates section of the textbook, I mentioned there's two methods, there's two ways you can approach these types of problems. One method in the past, when I was starting out in engineering, it gave me a lot of trouble. And the other method is the method that the book uses. But I think the method that I started out doing, which was just setting up a pure coordinate system, you can still do that and it will work fine. And so in this video, we're going to use both of the methods so you can see what I mean by these two methods. However, when you use a coordinate system, you might get a negative answer and the book says a positive answer, let's say, but you still may have the right answer because the way your coordinate system is set up, negative means the same direction as what the book's positive answer means, for example. So let's take a look at this problem so you can get an idea of what I'm talking about. The first method we're going to use is exactly how the book does it. Two cars start moving from the same point. One travels south at 60 miles an hour and the other travels west at 25 miles an hour. At what rate is the distance between the cars increasing 2 hours later? Okay, so this is a related rates problem. Remember, these types of problems, the characteristic is you're trying to find the rate of something, the rate of change of some quantity, but it's either hard or impossible to directly measure that quantity. But you do have the rates of change of either one or more other quantities that can be related to the quantity you're looking for with some sort of equation, like a geometrical equation or just any kind of equation. And so you can solve for that unknown rate of change. That's the idea. So what rates are easily measurable here? Well, the speed of the cars, right? The rate of change of position of the cars. So here is the starting point. They both start at the same point. One travels south at 60 miles an hour. The other travels west. So let me put it over here. We're going west at 25 miles an hour. At what rate is the distance between the cars increasing 2 hours later? So, okay, this car will have traveled further because it's going 60 miles an hour. So here is the car that's traveling south, and then the car that's traveling west doesn't go as far because it's traveling slower. Okay, and the question is, after 2 hours, so they start from this point, and exactly 2 hours later, what is the rate of change of, we'll call this D, the distance between the cars. What is the rate of change of this? What is D? Well, no, okay. What is S? What is ds dt after 2 hours at time is equal to 2 hours? Well, what we need to do is come up with a formula that relates the rate of change of position of this car and the rate of change of position of this car to the rate of change in position of this distance between the cars. So we'll call this the position of this car X and the position of this car Y. How is the position of this car and the position of this car related to the distance between them? Well, if this one's traveling west and this one's traveling south, we know that their travel directions are perpendicular, so we can use the Pythagorean theorem. X squared plus Y squared is equal to S squared. X is a function of time, Y is a function of time, S is a function of time. So we're trying to find ds dt. We're trying to find ds dt. So let's differentiate this equation with respect to time. And this is going to work because we're going to end up with like dx dt's and dy dt's. Well, we know dx dt. We know dy dt. We know the rate of change of x. It's 60 miles an hour. We know the rate of change of y, or y is 60 miles an hour, and the rate of change of x is 25 miles an hour. Okay? So to do this differentiation, we need to use the chain rule. What is dt of x squared? That's 2x. We'll do, instead of dx dt, we'll do x dot. That's like a symbol for the That's the first derivative of this function with respect to time, plus 2y y dot is equal to 2s s dot. Okay, now let's solve for s dot. Let's first divide both sides by 2. So s dot is equal to x dot plus y dot over s. So the rate of change of s at any moment in time is a function of the rate of change of x, the rate of change of y, but also the position at that moment of x and y and s. Interesting, right? So, okay, but do we have this stuff? Yeah, we've got every single one of these. What is the rate of change of x? What is x dot? It's 25 miles an hour. It's a constant speed. The rate of change of x is constant. The rate of change of y is constant, is 60. What about x, y, and s? Well, it's asking for s dot after 2 hours. So we can say 60 miles an hour times 2, 25 miles an hour times 2. So x is 25 miles an hour times 2 hours is 50 miles. Y is 120 miles. S is just the square root of this squared plus this squared. 130 miles. Okay, but this is where it gets tricky. This is where those two different methods come into play. It's the sign convention you use. So do we plug in negative 50 for x? Because it's going in like the negative x direction, right? I mean, this is the typical sign convention for x and y. Is this going like in the negative x direction? This is going the negative y direction. Well, for the method that they use in the book, the method that I've gotten comfortable with, you look at your formula that relates the variables. So it was this x squared plus y squared is equal to s squared. Like, hone in on that formula. Put a magnifying glass on that formula. What is that? That's the relationship for a triangle, for a right triangle, the sides of a right triangle. So we're looking at this as a triangle. So the first thing that should show you is that when it comes to like what we're going to plug in for x and y and s, that's going to be positive. Because when it comes to a triangle, there's no such thing as a negative side length, right? So for x, y, and s, we're just going to put it in positives. Now, what about x dot and y dot? We're looking at this as a triangle. Is the side length of the triangle increasing? This side length? Yeah, it is. It's getting bigger. So x dot's going to be positive. What about this side length? Is this increasing or decreasing? This is increasing, right? The cars are... Okay, and then as far as s dot, we're solving for s dot, so the final answer is going to tell us what that's doing, but we expect that to be positive increasing. So we're going to plug in positive x for the positive 25 miles an hour and positive 60 miles an hour. So, okay, s dot is equal to 50 times 25 plus 120 times 60 divided by 130. $65 miles an hour. Okay, now what if we had used the other method, which is where you set up a coordinate system, and let's say we decided to, we said, okay, this is the coordinate system, positive x, positive y. Well, we still draw this same diagram here because this car is traveling to the west, this car is traveling south, right? Well, you could say this. It's like this. X, Y. Well, we get this same x squared plus y squared is equal to s squared. We do the derivative with respect to time. We get this exact same equation for s dot. We use just trigonometry to get the magnitudes of x, y, and s. But in this scenario, what do we plug in? Well, at this moment in time, 2 hours later, this car is at x is equal to negative 50. This car is at x is equal to negative 120. S is just a magnitude. It's just the length of this line, right? S has no coordinate. It's a magnitude. It makes sense, right? What is S? S is the principal root of x squared plus y squared. It's always positive. So we're going to plug in x is equal to negative 50, y is equal to minus 120, s is equal to positive 130. What about the rates? This is moving in the negative x direction. We're going to put in negative 25. We're going to put in negative 60. So we get negative, 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 positive. So this is positive, this is positive. We get the exact same answer. Let's do another problem. A man starts walking north at 4 feet per second from a point P. 5 minutes later, a woman starts walking south at 5 feet per second from a point 500 feet due east of P. At what rate are the people moving apart 15 minutes after the woman starts walking? Okay. We've got point P, and then that this is 500 feet. Okay, the woman starts walking south. The man is walking north. And so, I mean, we can try and get an idea of after 15 minutes or after the, at the time we're interested in, who's farther above the starting line or who's farther from the starting line, but it doesn't matter. So we could just say, okay, that's where the man got, and the woman is here. Okay, so that's what we're interested in. Call this S, and we'll call this M for man and W for woman. We know that these are right triangles. Okay, so we're looking for S dot. How can we relate M dot and W dot to S dot? Well, we see there's a bigger right triangle. We know that this is 500, and we know that this side length is 500, and we know that this side length is M plus W. So we can say that 500 squared plus M plus W squared is equal to S squared. So 250,000 plus, okay, and we can expand this and we get M squared plus 2MW plus W squared is equal to S squared. So now let's take the derivative of this with respect to time. We get 0, this is 0, 2m m dot plus, this is one function of t, this is another function of t. We have to use the product rule here. So the derivative of the first, we'll say that 2m is the first function of t. Derivative of the first, 2m dot times the second, w, plus derivative of the second, w dot times the first, so 2m w dot. Okay. What is the derivative of w squared with respect to t? 2w w dot. Derivative with respect to time of s squared, 2s s dot. So now we just need to solve for s dot. Well, we can divide everything by 2, so we've got 2, well, no. S dot is equal to M dot plus M dot W plus MW dot plus WW dot. And we can clean this up a bit. Let's factor out the M dots and the W dots. So M dot M plus W plus W dot M plus W. Oh, okay. So we can factor out an M plus W. So M plus W, M dot plus W dot. All right, great. So S dot, we divide both sides by S. There we go. That's S dot. So now we just need the M dot and W dot. What is, based on the method the book uses, so we know what M dot and W dot are. M dot is 4 feet per second, W dot is 5 feet per second, but do we use positive or negative? Well, we look at our equation that we made to relate the variables. It's this equation here. What is this based on? Like, what's the meaning of this? This is where it's triangles. It's geometry. So in other words, the W here and the M here represent the side lengths of triangles, right? This formula is relating. Well, it's relating this big triangle here, this big right triangle. So W dot, like, okay, so we have M plus W. They're combined for this side length. W dot, so the 5 feet per second, what is that doing to this side length? What is that doing in this formula? It's making this side length bigger. It's making this side length bigger. Same thing with M. They're going different directions, but they're both, as far as our formula is concerned, they're both making this side length bigger. So they're both going to be positive rates in this formula. And now the M and the W, for geometry, there's no such thing. We're not going to put negative M or negative W. They're both positive, right? As far as side lengths, this is a geometry formula, the Pythagorean theorem. So, okay, we know what M dot and W dot are. We just need M and W. How do we find M and W? At what rate are the people moving apart? 15 minutes after the woman starts walking. So a man starts walking north at 4 feet per second from a point P. Then 5 minutes later, the woman starts walking. So if we're looking at a moment 15 minutes after the woman starts walking, that means the man has been walking for 20 minutes. North at 4 feet per second. So 4 feet per second. He's been walking for 20 minutes. And in 1 minute, there's 60 seconds. So $4,800 feet. That's going to be M. Now the woman has been walking at 5 feet per second for 15 minutes. So 4,500 feet is equal to W. So, all right, we've got 4,800 plus 4,500, and then 4 plus 5. Oh, we need to solve for S. What is S going to be? S is going to be, we need to take M plus W squared plus 500 squared. We need to use this formula here to get S. So squared plus 500 squared 9,313. So, okay. About 9 feet per second. All right, now let's do the coordinate system method. What if we said that this is the positive direction? We use like a coordinate system. So what would happen? Well, we get the exact same formula here that relates the variables. The derivative is exactly the same, but now m is positive, w is negative, s is positive, the woman's rate is negative, the man's rate is positive. So this is negative, this is negative. So it's not going to give you the right answer. So I guess you would have to establish like this is the origin, this is x, y, and use like a position vector on the man and on the woman. And that should work. But you can see though, sometimes if you do the coordinate system method, it works, but other times it can get you into trouble. So it should work if you used a base point, an origin point, and used position vectors. That should work, because when you just have this, I think the problem with the way I have it set up here, and that's kind of the way I did it when I was starting in engineering. There's no x-axis when I do it this way. Where's the x-axis? This is a two-dimensional problem. They're 500 feet apart. That's the error there, doing it that way. But if you did, the woman this is her position at any moment in time, and then this is the man's position at any moment in time, and then you take the difference, you subtract this position from this position, and you get a different another vector that subtracts those two vectors. If you did it that way and you set it up right, that would work.